Picture yourself walking along a road drawn as a curve. At every smooth spot, there's a clear answer to a simple question. How steep is it right here? The road is rising or falling at some definite rate. Slide a tiny straight edge along the curve, and it tilts to match the steepness at each point. Gentle here, steeper there, then easing off. That local steepness is exactly what we're going to capture. But now a sharp corner. Just before the corner, the road heads downhill. Just after, it climbs steeply. Two different slopes meeting at a point. So at the corner itself, there's no single sensible answer to how steep it is. That single idea, a well-defined slope at a point, is the derivative. Smooth points have one, corners and breaks don't. Let's build it, carefully, out of something you already know. The humble slope between 2 points. Here's a smooth curve, and one fixed point on it. A, f of A, in blue. We want the slope of the curve exactly at this point. The trouble is, slope needs 2 points, and we only have one, so we cheat, temporarily. Add a second point a little way along, a plus h, f of a plus h in rows. The straight line through both is called a secant line, and its slope we can absolutely compute. Read it off. Rise over run. The change in height. F of a plus h minus f of a, divided by the change in x, which is just h. This fraction has a name you'll see everywhere, the difference quotient. Right now, with h fairly large, our secant is a poor stand-in for the true slope. Now the whole idea in one motion. Shrink h. Watch the rose point slide down the curve toward the blue one, and the secant swing, rotating, tilting, until it grazes the curve at just the single point. In the limit, it stops being a secant through 2 points and becomes the tangent line, touching at 1. And look at the numbers. As h collapses towards 0, the difference quotient settles on a single value. Here, exactly 2. That limiting slope is the slope of the tangent, and that number is the derivative of f at a. Let's write it down precisely. The derivative of f at a, written f prime of a, is the limit, as h goes to 0, of that difference quotient. Every piece earns its place. The fraction is the average slope over a step of width h, a secant. The limit shrinks that step to nothing, turning the average into the instantaneous slope right at a. Two ways to read the very same number. Geometrically, it's the slope of the tangent line, how steep the graph is at that point. And physically, it's an instantaneous rate of change. If f is distance against time, f prime is your speed at this exact instant, not the average over a trip, but the reading on the speedometer right now. And one caution built right in. That limit must exist from both sides. Approaching along negative h and positive h must give the very same value. If the two sides disagree, the derivative simply does not exist there. Let's actually use the definition to compute a derivative from scratch, what's called working from first principles. Every step is just algebra. Plug x squared into the definition. On top, f of x plus h is x plus h, all squared. Expand it. X squared plus 2x, h plus h squared. That leading x squared cancels the minus x squared. What's left on top is 2x h plus h squared. Every term has an h, so factor it out and cancel it against the h on the bottom. That cancellation is the whole trick. It clears the 0 over 0. Now it's safe to let h go to 0. The h just vanishes, and we're left with 2x. So the derivative of x squared is 2x, a clean, exact formula for the slope at every point. Let's do one that needs a fraction trick. 1 over x. Put both little fractions over a common denominator, x times x plus h. The top becomes x minus the quantity x plus h, which is simply minus h. So we have 1 over h times minus h over x times x plus h. The h on top cancels the 1 on the bottom, Again, that key cancellation, leaving minus 1 over x times x plus h. Now let h go to 0. The x plus h becomes just x, and the bottom is x times x squared. The derivative of 1 over x is minus 1 over x squared. Notice it's always negative. 1 over x always slopes downward. The same machine handles anything. Feed in the square root of x, grind through the algebra, and out comes 1 over 2 root x. Different function, identical recipe. Plug in, expand, cancel the h, take the limit. Here's the shift that makes derivatives powerful. That formula 2x isn't one number. It's a whole new function. At each x, it hands you the slope there. So let's watch the slope of a parabola become a graph in its own right. Up top, the parabola f equals x squared. Below it, an empty pair of axes waiting to record its slope. We'll sweep a point across the top and, at each x, plot the slope down below. On the left, x is negative. The parabola falls and the tangent tilts downhill, a negative slope. So the point below sits low, under the axis. As we cross the bottom of the parabola, the tangent flattens, slope 0. Then, on the right, the curve climbs and the slope turns positive, rising higher and higher. And the trace it leaves is a perfect straight line, the graph of 2x, exactly as the algebra promised. Negative, then 0, then positive. The slope of the parabola is genuinely a function all of its own. Now, a relationship worth burning into memory because it runs one way only. If a function is differentiable at a point, then it must be continuous there. A smooth slope forces an unbroken graph, but the arrow does not run backward. Continuous does not imply differentiable. A graph can be perfectly unbroken and still have a point with no slope. The classic witness is the absolute value function. Here it is, f of x equals the absolute value of x, a perfect V. It's continuous everywhere. You can draw the whole thing without lifting your pen, straight through the point at the origin. But test the slope at the origin from each side. Approach from the left with negative h. The absolute value of h is minus h, so the quotient is minus 1. Approach from the right, positive h. It's plus h over h, which is plus 1. Minus 1 on the left, plus 1 on the right. The two one-sided slopes disagree, so the limit doesn't exist, and the derivative at 0 is undefined. Watch a tangent line try to settle at the corner. It can't decide which way to lie. So the contrapositive is genuinely useful. If a function has a jump, if it isn't even continuous, then it cannot possibly be differentiable. No unbroken graph, no slope. That single implication rules out a huge class of trouble. Differentiability breaks in a handful of classic ways. Let's meet each one clean picture at a time, so you can spot them instantly. First, the corner. Two smooth arms meet at a sharp point, and their slopes don't match, minus 1 and plus 1. The absolute value at 0 is the textbook case. Continuous, but no single tangent. Second, the cusp. A sharper cousin of the corner. Here x to the 2/3 power. Both arms come screaming into the point almost vertically. One plunging, one soaring. The slopes head to minus and plus infinity. So again, no derivative. Third, the vertical tangent. The cube root of x at 0. The graph is smooth and unbroken. But at the origin, the tangent line stands straight up, perfectly vertical. Its slope is infinite, and infinity isn't a real number, so the derivative is undefined. And fourth, the worst offender, a jump. The graph leaps from one level to another, so it isn't even continuous. And by the rule we just proved, no continuity means no derivative. It fails on the most basic ground of all, Your turn. Use the definition, first principles, to find the derivative of x squared plus 3x. Set up the difference quotient. Expand, cancel the h, take the limit. Pause the video, work it through, then come back. Here's the walkthrough. Substitute into the definition. Expand the top. X plus h squared gives to xh plus h squared, and 3 times x plus h gives an extra 3h. The x squared and 3x both cancel their partners. Every surviving term carries an h. So factor and cancel against the bottom, leaving to x plus h plus 3. Let h go to 0, and the derivative is 2x plus 3. If you got that, you've genuinely mastered first principles. One more, quicker. Is the absolute value of x minus 2 differentiable at x equals 2? Think about the shape before you compute. Pause and decide. It's the same v, just shifted, so the corner sits at x equals 2. And a corner is a corner. The left slope is minus 1. The right slope is plus 1. They disagree. So no, it is not differentiable at 2, even though it's perfectly continuous. Trap 1. The big one. Assuming continuous means differentiable. It doesn't. The absolute value is continuous everywhere, yet has no slope at its corner. Smoothness is a stronger demand than unbrokenness. Trap 2. Forgetting the arrow that does hold. Differentiable always implies continuous, so its contrapositive is a free test. If a function jumps, stop. It can't be differentiable. Trap 3. Checking only one side at a boundary. The derivative is a limit, so both one-sided slopes must exist and match. At a piecewise join, always test left and right separately. And trap 4. Treating a vertical tangent as fine. A slope of infinity is not a real number. The cube root of x at 0 looks smooth, but its derivative there is undefined. Let's lock it in. The derivative at a is the limit of the difference quotient, the slope between 2 points, as the 2 points merge into one. Read it two ways. The slope of the tangent line and the instantaneous rate of change. Same number, two faces. It's a one-way street. Differentiable forces continuous, but continuous never forces differentiable. The absolute value proves it, and it breaks in 4 familiar ways: a corner, a cusp, a vertical tangent, or an outright jump. Hold these 4 lines, and differentiability will never catch you off guard.